Welcome back. Today we are looking at section 3.2b, our second day of section 3.2. We are solving systems of equations, and this focus today is on the algebraic process called elimination. So we've been looking at solving by graphing and solving using substitution, which is an algebraic method. Today we're going to focus on the elimination method. So our first step says to identify the variable that has opposite coefficients in the two equations. You may need to use multiplication to create the opposite coefficients. So let's look at our first example here and identify which variable has coefficients, those front numbers, that are opposites. So you'll notice here that the x's, I guess I'm going to have to redo my board, 1 second. All right, let's try that again. Notice that the x's have opposite coefficients. So this is what we're going to eliminate. We're going to eliminate our x's. Step 2 says to add the two equations so that one variable drops out. So when we add our two equations together, 3x plus negative 3x, we have 0 x's. 1y plus 2 more gives us 3y. And 19 plus 11 is 30. So now we can do step 3. Solve for the remaining variable. If we divide both sides by 3, our remaining variable y ends up being 10. Once we know that, it's really like the substitution process. We're going to plug this answer back into one of our original equations and solve for the other variable. Now you can use either equation. And we have y being 10. So let's say we plug it back in here. Now we have 3x plus 10 equals 19. Subtract our 10 over, we have 3x equals 9, and divide, we end up with x being 3. So my point where these two lines would intersect has the coordinates 3, 10. Now it is important to make sure that we haven't done anything incorrect, so let's check our answer. We're going to put a 3 and a 10 in to both of our equations for our x and y's and double check that it really does work. For the top equation, 3 times 3 is 9. 9 plus 10 does equal 19, so that one works. For our second equation, negative 3 times 3 is negative 9. 2 times 10 is 20. Adding those, we get 11. So it does work in both equations, so it is the correct solution. All right, let's try another example. Notice on this one that we have a 1y in both of these places. So we could try to eliminate the y's, but we need them to be opposite coefficients. So here's a case where we might have to do some multiplying to get one of them to be opposites. We can choose to multiply either equation. I'm going to choose the first one, and I'm going to just multiply by a negative 1. That gives me a negative 2x, a negative 1y, and a negative 4. Now when I add it to my second equation, you'll notice that the y's will drop out. We have a negative y plus a y, that is 0. So adding these, we get 1x. Adding the negative 4 and 7, we've got a 3. So our x coordinate is 3. And now we can plug that back in. Again, we can use either equation. I'll just dump it in the top one. And to figure out our y value. So we have 2 times x, which we now know is 3, plus y equals 4. So 6 plus y equals 4. When we subtract the 6, we get y equaling negative 2. So our ordered pair would be 3, negative 2. Again, you can check that in the original equations. If we put a 3 in for x and a negative 2 in for y, we have in the top one 6 plus negative 2, which is 4. That works. Checking the bottom equation, 3 times 3 is 9, plus a negative 2 is 7. So it does work in both. It is the correct point of intersection. All right, our last two examples here, you'll notice we don't have opposites yet. So we are going to have to use some multiplication. Sometimes we might have to multiply both equations by a number, and it doesn't have to be the same number. Sometimes we can get away with just multiplying one. So Let's analyze this. If we were going to try to eliminate our x's, the closest we could do to get a 2 and a 3 to match would be to make them 6's. So we could times the top equation by, say, a 3 and the bottom equation by a -2. That would make the top equation have a 6x, the bottom equation would have a -2x. But that requires 2 multiplications. So let's look further. If we try to eliminate our y's, we could get our bottom equation to be a 3y by multiplying by a 3, and then we would have opposites. So this route allows us to do 1 multiplication instead of 2. So we'll go ahead with that option. I'm not going to do anything to the top equation. It's fine the way it is. I'm going to multiply the second equation by a 3, and be sure that you multiply all the pieces. So 3 times 3x would be 9x, 3 times y is 3y, and 3 times 32 would be 96. Now when we add our equations together, our y's, which we were trying to make be opposites, are in fact opposites. So we can add them together and the y's will drop out. We end up with 11x equaling 99. When we divide out the 11, we've got x being 9. Now we have to do a substitution. And again, we can plug it back in for x into either equation. I'm going to dump it in the bottom equation this time because I am trying to find y, and there's a nice single y in that bottom equation. So 3 times x, which is 9, plus y equals 32. 3 times 9 is 27. If we subtract 27 to the other side, we've got y equaling 5. So correct solution would be the ordered pair 9, 5. Our x value was 9 and our y value was 5. And again, we could check that, plugging them back into our original equations. For our last example, again, we are trying to get one variable to have opposite coefficients. So this is another one where I could get these y's to drop out. Okay? I am going to work through this one as if I were having to multiply 2 equations, just so you can see what that one's like. If we were trying to eliminate our x's, I could multiply the top one by 2, which would make this a 10x, a 2y, and a -6. Again, distributing to all of them. That means I have to get a -10x for my second equation. So I'm going to have to multiply this one by a -5. And I could have put the negative with the 2 and multiplied that into the top equation and then had the +5 for the bottom equation. Either way would work. Multiplying through a -5 gets me -10x, +15y, and then 5 times 26. Let's work that out. We've got 30, so 130. And it's a -5 times a +26, so it's going to be negative. Adding our equations together, our x's drop out. We've got 17y equals -136. Okay, go ahead and grab your calculators. We're going to divide out a 17. All right, checking, you should end up with y being -8. All right, let's plug that back in. Again, we can put it into either equation. Let's say I pick the bottom one. We have 2x minus 3 times our y value of -8 equals 26. -3 times -8 is +24. Subtracting 24 to the other side gets us 2, and dividing gets us a 1. Okay, so we end up with our coordinates 1 for x and -8 for y. Now again, did we have to do that equation multiplying both? No, we did not. We could have multiplied the top equation by a 3 and gotten our y's to cancel out right away. But I wanted to show you one example where you may have to multiply both equations by a number. It does not have to be the same number. You just have to make sure and multiply it to all the pieces of that equation. All right, you guys are going to be working on a worksheet for 3.2b.